And now let's start a new part where we will work not with a simplified model of a planar 2D robot, but with a real 6 degree of freedom industrial manipulator. This robot is called the Puma 560 robot. And it is a very classical device that we can find in many industries worldwide. It has been manufactured for many decades actually, and it has the advantage of having been studied in depth by several universities. Okay, so it's one of the robots from which we have more information in the world. Okay. So we have data about this robot, about its geometry, about its moments of inertia, which are also important. We have information about the motors, the electrical motors that drive the joints. We have information about the sensors. We have such a detailed model that we can very realistically simulate it, and that's why we are bringing here to the classroom. Okay, and there's another advantage, and if you take into account, if you remember the robot with which you have been working in the last couple of weeks of the course, you might remember that in Robot Studio there is a specific robot called IRB120, which is the one that we have in the laboratory, that has many features that are similar to this robot. Okay, well, the joints are organized in the same way as in this robot. Okay, the IRB120 has a similar joint organization as the Puma 560 robot. It has a waist, sort of a waist, so it has an initial degree of freedom around this vertical axis. Then it has something that could be called a shoulder, because it's a degree of freedom around an horizontal axis. It also has another horizontal axis in here, which can be called an elbow, okay, because we can figure out the arm of a human being. And then it has 3 axes of rotation here in the wrist, all together and joined by a common origin, right? So this 6 degree of freedom are organized in this way here in the Puma 560 and also in the IRB 120. There are many other industrial manipulators, and it is very common to have this configuration. For some reasons, one of them is practical, but other reasons are purely mathematical, as we will see in this chapter. Well, okay, so it's not hard to see that, okay, there are 6 coordinate frames, right? And these are presented in here. There are 6 joints. Okay, this is the frontal view of the robot on the right. And the nice thing is that we are going to work with a model of the Puma 560 robot in MATLAB. The model is included, in fact, in the robotics toolbox that we have been using already. Okay, but after the regular loading of the robotics toolbox that often comes with the calling of startup error RVC, then after that we have to load the specific robot model by writing MDL_Puma 560. Okay, and from that moment there's a new object or variable that appears in the MATLAB workspace called P560. Okay, so this is a new variable. But more than a variable is an object, and an object is like something more powerful than a variable, because it can have values, okay, like for example or P560 dot links. Okay, it has some values which are the links that form the serial link object that is inside it. Okay, but it also has methods like the forward kinematics method that we have introduced before. Okay, and the point is that in order to take a quick peek at the contents of this object, we can just write in MATLAB P560 and enter. MATLAB will give us this information in return. First of all, this table appears with what is easy to identify as a set of Denavit-Hartenberg parameters, right? So there are of course 6 joints, so there are 6 sets of parameters in here, yes. And what is more remarkable or interesting is that the theta variable in each of the joints is actually the time varying variable, the non-constant variable. This is equivalent to say that all the joints are revolute, okay, are rotational. There are no prismatic joints, right? But if we remember from the first discussion, not having any prismatic joint does not imply that dj must be 0 for all joints. So there are specific values that we associate to the displacement of the coordinate frame along the axis of rotation of the joint. Okay, so these are non-zero values that are necessarily to perfectly describe the geometry of this robot. There's some extra information right in here, right? 1, 2, 3, 4. This information is the base of the robot. Okay, so in order to understand this, first remember that this is an homogeneous transform matrix. Okay, and an homogeneous transform matrix can be used for several things, and one of them was just to identify the location of one coordinate frame in space, some coordinate frame like this, with respect to another coordinate frame like this. Okay, in the same way as we use a vector to locate a point in space with respect to some coordinate frame. Okay, so in a way, locating B with respect to O is equal to stating the location of, let's use capital B, of the location of coordinate frame B with respect to coordinate frame O. Okay, so, and what coordinate frames are locating, is locating this matrix in here? Well, it is identifying the position of the base of the robot with respect to the universe. Okay, so now we have to figure out that there's a robot in here, that the base is in here, and the links of the robot start from the origin of the coordinate frame B. Okay, in the previous example we assumed that the base of the robot was exactly at the origin of the universe coordinate frame. But in practical applications, this is not a sensible way of doing things, because imagine some situation as simple as having 2 robots cooperating together. Okay, so if we say that the base of the robot is the universal coordinate frame, then if we have 2 robots, which of those is going to be called the universal? So in many situations we need the universal coordinate frame, the 0 coordinate frame, to be away from the base of the robot, and this is what it is illustrated here. So when we have a coordinate frame in here, a homogeneous transform matrix in here different than the identity, we mean that the base of the robot is not at the coordinate frame of the universe, and that this homogeneous transform matrix will tell us what is the location of the base of the robot with respect to the universe. And now some more about the new robot called Puma 560. And in this slide we just observe that okay, there's a 3D plot, a set of 3D plots of something that if I don't tell you, you would have never thought that it is a robot, but it is. Okay, so this is a representation of the robot with all its joints. Okay, so the first joint is around the vertical axis, so it's not depicted here, but the second joint is this one, is easy to see it as a shoulder. The third joint is easy also to see as an elbow. Okay, and then finally the three remaining joints represent the end effector of the robot. Okay, so what happens here? Well, this depiction of the robot it might seem not intuitive, but it is a nice way to represent a robot, because you are visualizing just the things that are important for the kinematics, which are actually the axis of rotation. So this is an axis of rotation, this is another one, vertical one, this is another axis. So it is interesting to have a simplified representation of the robot where only the axis of rotation appear. And the axes of rotation are not coincidence, so there are distances among them, and these distances are due to the fact that the Navitt-Hartenberg parameters are not zero, so we must make displacements to go from one axis to the next. Okay. Well, once that we have a slight idea of what this plot means in 3D, well, not forgetting that these three axes are X, Y, and Z. This is important. Okay, once we know that, we can represent the robot at different configurations. Okay, these configurations, which are just like poses, they are just like positions of the robot, are identified by the value of the angles of each of the joints of the robot at a given time. Okay, so as the robot has three angles, we can call them Q. There is an equality between generalized coordinates that in physics are normally represented by Q. This is the vector of generalized coordinates, and there's an equivalence between the vector of generalized coordinates and the set of values of all the joints of the robot at a given time, which are theta 1, theta 2, theta 3, theta 4, theta 5, and theta 6. Okay, so using this correspondence, we very simply can understand that this vector of 6 elements represent the present value of each of the joints at each of the axes at a given time. And the toolbox, initially when we load it, it appears with a set of Q vectors preloaded in memory. Okay, first of them is QZ, where all values of theta are equal to 0. Then QR, with these values, 0 for the first joint, pi over 2 for the second, minus pi over 2 for the third, 0, 0, 0. And this is called the ready position, and it happens when the arm is straight and vertical. It corresponds to this image in here. right? So someone might think that by looking at this image that the value of all the coordinates are equal at a given time, but this is a bit misleading, okay? Forget that not only the thetas determine the position of the robot, but also the other Navitt-Hartenberg parameters that are not visible here. They were visible in this previous table. Okay. Well, I hope this comment is not too complex, but okay. So there's a third set of values called QS, which correspond to what we call the stretch position. Okay, the stretch position because it happens when the arm is straight and horizontal, and it corresponds to the values of theta 1 equals 0, theta 2 equals 0, theta 3 minus pi over 2, 0, 0, 0. Okay, and this is visualized in here. So again, observe that in order to have the robot totally flat, totally stretched in the xy plane, we need not all the variables to be 0, but we need this pi over 2 element in here. Why that? Because of the alpha that we have here that introduce rotations from one coordinate frame to the next, or from one joint to the next, through the alpha parameter. I mean rotations that are not present in the Q variables. Okay, and there's a final predefined variable called Qn, and this is the nominal position, and it corresponds to the situation in which the arm is at dextrose working pose. Okay, so dextrose, this idea of dextrose is like, let's take a look at the shadow that is projected down here. Okay, if it were the hand that is the shoulder and the elbow of a man or a woman, it is clear that that person would be working with their right hand. Okay, so that's because this joint is to the right of this joint from the perspective of the robot. Okay, so that's why we call it dextrose. The robot could flip around perfectly. I mean, we could turn it completely to this position, okay, and then make it turn from the waist another 120 degrees, and we would obtain totally the opposite shadow. Okay, so the robot has two configurations that are very similar but not exactly the same. Well, still QN is interesting because many robotic applications start with the robot at the QN values. Okay, this is a practical situation where we leave space to introduce new parts to be accessed by the robot. Okay, so some joints of the robot are elevated with respect to the working part, and that leaves space for the tools and the new parts to enter the system. Okay, so in summary, zero angle, ready position, stretch position, and nominal position. So now let's talk about the forward kinematics of the Puma 560. Okay, talking about forward kinematics is just talking about a function that receives as an input the vector q of the present value of all the coordinates, that is, all the theta angles of the robots, and this operation computes the homogeneous transform matrix that changes coordinates from the end effector to the, I would say, zero coordinate frame, but if someone of you is really aware of what is going on, they would say no, this is about B, not zero. Okay, for me, for the general discussion, it is better to simplify and write it like that. Okay, so How do I compute the forward kinematics in P560? Well, as I said before, a lot of information of the Puma robot is included in the object that we have loaded into MATLAB. So with this information, MATLAB can itself compute the forward kinematic by calling the function P560.fkine. And then, as I said before, the forward kinematics is computed for a specific value of the generalized coordinates. So I have to give some value of the coordinate. So I could use the vector QZ that was defined in the previous slide to compute that function, and this would give me this 4x4 matrix, which is the homogeneous transform matrix from the end vector to the base of the robot. And now there's an operation that it is interesting to do, and is, let us for the first time change the base of the robot. Okay, so for the first time we are going to separate the robot from the universe coordinate frame to another coordinate frame that will be the new B coordinate frame according to our notation. Okay, so separating this is done by assigning a homogeneous transform matrix to the component base of the object P560. Okay, so we are assigning this matrix that, as we all know, here we have an identity matrix. Here we would have these numbers. So here we have 30 by the size of an inch actually, so I'm not filling the whole thing in. And okay, so this is the homogeneous transform matrix. This corresponds just to the vertical displacement of 30 inches along the Z direction. So if you want me to be more precise, I'll write exactly with where the B coordinate frame is, and I would we would happily use a different color for this. So there's some distance which is called 30 inches. Okay, 30 inches. That's why we multiply this by this, because this is the size of an inch in meters. And then, okay, so some 30 inches upwards in the Z direction, that we would find our newly located base coordinate frame. Okay, so this is what we are specifying here. And now let's make a second try, which is, let's reassign the base of the robot somewhere else. Okay, so somewhere else, which is actually a translation of 3 units upwards. Okay, so this new situation would be something like that. I'm going to write it here to the right. So I would have here the initial coordinate frame X, Y, Z of the universe. Now let us think that there is a vertical quantity called vertical distance of 3 units that would redefine the 0 coordinate frame of the new the origin of the new coordinate frame. But after that, there should be a rotation around the x-axis of pi. So the new coordinate frame will result in this being the new x-axis, this being the new z-axis, and this being the new y-axis. Okay, so this would be the new base or B coordinate frame. Okay, and the product of these two matrices is assigned to P560.base. Okay, and what happens here? Well, the thing that we have is that Now, if we compute the forward kinematics of the robot with the coordinates qz, we have this matrix. And the nice thing is that, remember that a moment ago we computed exactly the same P560 F kine qz, and we are actually computing the same thing. So the two yellow highlighted pieces of text actually are computing the same thing. Don't you agree? Then let's remove some of the dirty material that we have in the slide. And don't you agree that this line is equal to this line, but the results are not equal, okay? Because there is some change in the rotation matrix. Well, okay, this tells us that the forward kinematics compute in MATLAB is actually the homogeneous transform matrix from the end effector with respect to the universe to 0 and not with respect to the base. Okay, that's a very important thing. If the homogeneous transform matrix were defined with respect to the base, then it would not change with the change of the base, but is referred to the universe. So the effect of changing the location of the base changes the relative location of the end effector with respect to the universe. Okay. So, and there's a final very important operation, which is the inverse kinematics. Again, it is a calculation that can be defined if we remember what is the forward kinematics, which is starting from Q, we have A, E, 0. Well, the inverse kinematics is just the inverse operation starting from A, the homogeneous transform matrix of the robot, of the end effector with respect to 0, it would compute the set of Q values, that is the angle of each of the joints that will result in the end effector having the pose described by 0AAE. Is that sentence clear? I mean, given a pose, a desired pose, if we want the hand of the robot to be somewhere defined by A, then the inverse kinematics will compute the values of all the angles that will make the hand reach that point. This is something very intuitive, and we are doing that all the time as humans. Think of our hand. Sorry for plotting our hand as a robot hand, it looks like it. But imagine that we are just touching this frame with our hand. For example, that we are cleaning the frame, and we want to move the hand along the surface of that frame in order to clean it. What is our brain doing while we are cleaning that wall? Well, we are solving the inverse kinematics problem, because the position of the hand is what we call the desired position. That is, this is where I want my hand to be because I want it to perform some task. And in order to do that, I need to fix my joints at some angles that, putting them all together, sorry, this 2, 3, 4, and so on, that putting them all together, they cooperate to bring the hand to the desired position. So we have joint angles. Okay, do you agree with me? The hand cannot fly. The hand can only reach the desired position by moving each of our joints one by one to a specific value, right? and those specific values are computed by the inverse kinematics. So in a way, our brain starts with a desired position and it computes the values of each of the joints. Is that clear? So this really summarizes what we have. So assume that we have a desired pose, and to place the end effector in that pose, we must give specific values to the q coordinates. And this is an operation that is called the inverse kinematics, and it is generally performed using the if kine function, right? As we said before, the if kine function should receive an homogeneous transform matrix as a parameter, and as a return it will give a vector of generalized coordinate. As we are talking about the Puma 560 robot, okay, so the function call should follow again this syntax. It might sound strange to you, but this is used in object-oriented programming. Not meaning that we have to learn any object-oriented programming at all. It's just we are using a specific syntax. Okay, the problem here is that the mathematical equations that gives us joint values for a desired hand pose is a mathematically complex problem. It's somewhat hard to solve. Sometimes it is impossible. Okay, why could it be impossible? Well, imagine that you yourself with your body, you want to clean this frame in here, so it's simply not reachable, and not reachability is a condition for the inverse kinematics problem to not be solvable. But sometimes it's not the only condition. Okay, there are other reasons why it is not practicable, and some other times there is a solution, but it might not be unique. There could be multiple solutions. And now we will show an example of a multiple solution situation of the inverse kinematic problem. So let's start with this variable qn that we all know. It is preloaded in MATLAB, and it has a set of values of the generalized coordinates that will set the robot in the nominal position, right? So imagine that we compute the direct kinematics. Okay, this is the direct kinematics. Okay, sorry, because we are not actually using that word. It's forward kinematics. So we compute first the forward kinematics, and it's like A, K, and then it gives us a matrix A. All right. So this matrix A, or called T in this case, it gives us this matrix, and this is assigned to T. So now let's pick up again this matrix T and assume that we desire the robot to reach the pose represented by this matrix T. So what would be the generalized coordinates that would reach that pose? Well, logically, if we computed this pose starting from Qn, the inverse kinematics of T should be Qn again. It's like undoing the computation or doing it backwards. But what comes here in some way as a surprise is that when we compute the inverse kinematics starting from T, we obtain a set of values that is totally different from those that we had at the beginning. So we don't get Qn, we get Qi. Okay, so there's ambiguity. Well, not really. I mean, what is happening here is that there are different ways of getting a desired pose of the end effector. Okay, so there are different choices. But before going in there, I have to roll back a little bit and take a look at this function name. Okay, this is not the function I introduced before. This is not if kine. It's a bit different. It's I kine 6s. Well, let's just for the moment admit that specifically for Puma 560, we will prefer this function instead of the previous one, because the previous one is a generic function that will iterate, and it will take long to make its computations and possibly make errors. But this Ikine 6s is a specific function for robot Puma 560 and robots that are very similar to it, that is much more efficient and has less error. Okay, so this observation, well, this slide is just reminding us what we have just seen, is that there is ambiguity in the sense that starting from Qn, the forward kinematics will give us a matrix that if we apply to it the inverse kinematics, we don't get Qn as a return. So there is ambiguity. We have said before that ambiguity means different ways of reaching the same position. But we can see this graphically actually. The set of coordinate values in here take the robot to this specific location of the coordinates, okay? This is a end effector coordinate frame, right? And please look at the shadow. No, it looks like left-handed in the sense that the elbow opens to the left of the robot. Now let's take this configuration, which is totally different. It might seem similar, but look at the shadow. It is right-handed. Okay, so in order to get to from one position to the next, we really have to turn around the whole arm, invert it, and then make another twist of 180 degrees to have this. So these two positions of the robot are very different, but they reach exactly the same final coordinate frame, okay? And this is why there is ambiguity, because there are different sets of coordinate values that would reach the same final end effector coordinate frame. So how do I solve this? Well, okay, as the function Ikine 6s can give us these different solutions for the problem, we might choose among the possible solutions some specific ones, or ones that have specific features, and these are like specified by using these letters in simple quotes. Okay, so the first letter is here appears as R, but it could be perfectly either R or L, meaning right or left, and U would be a choice between U and D, okay, corresponding to up and down, right? And what does this mean? Okay, well, the first letter would be interpreted as left-handed or right-handed, and this is clearly seen by the shadow projected on the floor. This would be clearly a left-handed robot, okay? Because think of a person picking something, and if this is the shoulder is opening to the left, and this would be a right-handed person, okay? So the ambiguity between those images is solved by specifying L of R. If we specify L, we are referencing the first image. And elbow up and elbow down is also important. Sometimes I can reach the same coordinate frame by turning the elbow of the robot in one of those positions. So in this first position, the elbow angle opens downwards, and in this position the elbow open upwards. But finally both configurations will reach exactly the same final end effector position. Okay, so in order to solve this ambiguity, I can specify up or down. Please look at here that the elbow is up in both cases, so the ambiguity in here is not solving anything. But if at a given moment we had something like this, this would correspond to the D option. So finally, by calling function ikin 6s with the options R and U, we are telling MATLAB that from all possible solutions, this should be the one that prevails. Okay. Still, ikin 6xs will never have infinite solutions. Okay, it might have several solutions, but always within a discrete set, right? Well, there could be some degeneration. Okay, so I'm saying too happily that they're not infinite solutions. In some situations there are, but the normal situation is that there are 2 or 3 solutions. So let's stop a little bit discussing some of the limitations of the inverse kinematics. The inverse kinematics follows an explicit formula. In other situations, there's no such formula, and an iterative algorithm is required. Iterating should remind us something from the numerical methods for engineering course, where in order to solve some problems, we cannot just apply a formula. We have to implement an algorithm that after many iterations will come close to the solution. Well, okay, so the inverse kinematics in general needs a iterative approach, right? But even in the case where it can be solved with an explicit formula, there can be ambiguities. We are going to summarize here what are the conditions for the existence of an explicit formula for the inverse kinematic problem. Okay, if the robot has 6 degrees of freedom and the wrist of the robot have 3 axes that intersect at the same point, for example, this is the z-axis of one joint, this is the z-axis of the second, and this is the z-axis of the third, they all intersect at the same point. Okay, if these 2 things happen, then there is a formula that can solve the inverse kinematics problem explicitly without having to iterate. And this is very important in robot control. This is so important that this is the reason why the Puma 560 has been designed with this particular geometry. So in other words, the robot has been designed for mathematics. Now, what do you think? The human hand fulfills those conditions. Has the human hand been designed for mathematics? Or has the human hand been designed for making things easier for the controller that we call the brain? Okay, here we have these 3 axes of rotation around the wrist, and then we have the elbow, and then we have the shoulder. It seems to me that nature also knew a little bit of mathematics when it took the decision of building our joints the way they are. Isn't it curious? Okay, I'm going to stop here, not going into singularities in this video.